The Nernst equation tells us the voltage created by each ion species based on its concentration gradient across the membrane. Neurons maintain steep concentration gradients. Sodium is high outside, potassium is high inside. These gradients store enormous electrochemical potential energy. The sodium-potassium pump actively transports 3 sodium ions out and 2 potassium ions in, consuming ATP. This uses about 70% of the neuron's energy. The Goldman-Hodgkin-Katz equation combines all ion gradients to give the resting potential of about negative 70 millivolts, dominated by potassium permeability. Voltage-gated channels contain voltage sensors that change conformation when the membrane potential crosses threshold, opening the channel pore. The Hodgkin-Huxley equations model the dynamics of voltage-gated channels. Each channel type has gating variables that evolve according to voltage-dependent rate constants. When voltage stays below threshold at negative 55 millivolts, the depolarization decays passively. This is the subthreshold regime. Above threshold, sodium channels open, causing sodium influx. This depolarization opens more channels in a positive feedback loop, creating an explosive all-or-nothing spike. The falling phase occurs as sodium channels inactivate and potassium channels open. Potassium efflux repolarizes the membrane, often causing a brief hyperpolarization. The action potential has a stereotyped shape, about 1 millisecond wide, 110 millivolts in amplitude, determined entirely by the kinetics of ion channel gating. The Cable equation describes how signals propagate through dendrites. Space and time constants determine how far and how fast signals travel. Dendrites actively shape signals. Dendrites perform sophisticated computations, spatiotemporal summation, dendritic spikes, and branch-specific processing. Each dendritic branch is a computational subunit. STDP is a learning rule where the timing between pre- and postsynaptic spikes determines whether the synapse strengthens or weakens. Pre-before-post strengthens, post-before-pre weakens. When the presynaptic spike arrives before the postsynaptic spike, calcium enters through NMDA receptors. High calcium activates KM2, leading to LTP and synapse strengthening. When the postsynaptic spike arrives first, the presynaptic input finds the neuron already depolarized. Moderate calcium levels activate phosphatases, leading to LTD and weakening. Neuromorphic hardware implements the same differential equations in silicon. Ion channels become transistors. Membrane capacitance becomes chip capacitance. The physics is isomorphic. A single neuron embodies molecular precision, dendritic computation, and local learning, all running on chemistry at picojoule per spike efficiency. Biology found the optimal solution billions of years ago.